Welcome to the Apron Academy. This video is specially designed for the dietitian in training, also known as the RD-to-be. This episode, I'm going to be talking about riboflavin. So riboflavin is also known as vitamin B2. So I know this structure looks kind of daunting, but we're going to break it down. You can see that it's already kind of broken down, but I want to clarify that this whole entire thing is FAD. This is one of the cofactor forms of riboflavin, and FMN is the other cofactor form. So there are two cofactor forms. These are also known as flavoenzymes or flavocoenzymes. But for now, just know that these two, FAD and FMN, are the cofactor forms for riboflavin. So this section of the structure is the riboflavin part. You can see that it's a little smaller. This FMN adds on this. And then we have AMP, and all together this makes FAD. So where can we find it? We can find it in milk, eggs, can find it in meats and leafy greens. And I want to point out that the milk and eggs is in the free riboflavin form. So if we look back to this structure, it's ingested as this smallest form. The leafy greens and meats often found in the FAD form, so that's the biggest structure. So as we have talked about in many of our videos, when it's in this bigger form, in order to absorb it, we have to get it into the smaller form. So thankfully, when we eat milk and eggs, it's already in that smaller form. With these other things that are in the FAD form, we have to break it down. So let's talk about how we can do this. So this is one of these things that you do have to memorize the whole thing. But if you look at the big little blocks, the FAD to FMN, and then FMN to riboflavin, we can understand that because we're going from biggest to a little smaller, then to the smallest. So that's how we want to absorb it. And then we have these enzymes here that help us do that. FAD pyrophosphate, and then FMN phosphate. So I want to take a minute. In some of our videos, I have this little drawing. It's if we have the human intestines, we've chopped it in half, and we're looking down the middle. So it won't look exactly like this in a real human body, but imagine that this is your outside of your intestines. Then as you're looking inside, there are all these villi, and on the villi we have these enterocytes, and they are our intestine lining. So if I'm going to kind of zoom in on one of these little guys, I have this. So FAD, or riboflavin, is absorbed by two mechanisms. It's absorbed through this luminal side of the enterocytes, so coming into the enterocyte, and then also when you have the higher levels, well, let me repeat myself. So I have these two mechanisms. The first one is with this luminal side, but we have a little transporter, so almost like a gatekeeper right here. And these transporters are called RFT1, RFT2, and RFT3. Many times the RFT2 is the one that's on the intestines, so I'll just write this here. But you do have all these transporters that get the riboflavin to other areas of the body. If you have FAD, basically it's able to get into the cell and out of the cell with this transporter. And the second mechanism is through diffusion. So that's when you have very high levels of the riboflavin. It's able to pass straight on through without the help of one of those transporters. So once it gets in the body, it doesn't just float free. There's not free floating. Try saying that 5 times fast. There's not free floating riboflavin in the body. It is bound to albumin or an immunoglobulin loosely. It's bound to that loosely. So then it's able to go to the liver, then into the blood and to the rest of the body. So let's talk about when it gets to the liver. So with most of our micronutrients, we have them in this smaller form, and in order to use them, we have to get them back to the bigger functional form. But we can't just reverse this. Can't just use these same little enzymes to get it back to FAD. We have to use something else. So another little mechanism, I guess, that we need to know is this one, where we're getting riboflavin back to FMN all the way to FAD. So the first enzyme from riboflavin to FMN is flavokinase, and then from FMN to FAD is FAD synthetase. So that is, once it gets into the liver, we have to remake these cofactors. Now I want to talk about the functions. So there are 170 plus reactions that riboflavin plays in our body. So some of these are DNA repair, fatty acid oxidation. It helps with the vitamin B6 coenzyme synthesis, detoxification, immune function. I could go on and list everything, but the essence is it's needed everywhere. So you can see here it is in the electron transport chain, here it is in the Krebs cycle. We need riboflavin. But what happens if we don't have enough? So there's not a specific deficiency if you don't have enough for riboflavin, if you don't have enough riboflavin, but it presents like pellagra or a vitamin B6 deficiency. So you can check back on our niacin and B6 videos and look at those deficiencies, but it presents similarly. So things like dermatitis, anemia, muscular weakness, soreness of the mouth and tongue, burning eyes, superficial vascularization of the cornea, so affecting our eyes more, and then neuropathy. It is important to note that riboflavin is needed for early development. So we can tell this because there's a specific riboflavin binding protein that's increased only during pregnancy so that the fetus receives enough riboflavin. So the fact that a very specific way to get riboflavin from the mother to the baby just shows that riboflavin is needed in that early development. When a baby is born preterm, we often see that it does not have enough riboflavin. And then even in mom's breast milk, riboflavin is found, showing that there is a continual need of riboflavin as the infant develops. So with a deficiency, again, there's increased risk for anemia, even cancer and cardiovascular disease, and neurodegeneration. neurodegeneration. So now, finally, I want to talk about a possible genetic disorder. So the one I want to talk about today is called multiple acyl-CoA dehydrogenase disorders, or MAD. These mutations happen in the electron transfer flavoproteins. So it's when this beta oxidation cannot make enough to send to the electron transport chain. So this acetyl-CoA dehydrogenase, it is a major source of energy for the heart and muscle and liver. So if we have a deficiency of riboflavin, it would cause symptoms in these organs. So heart issues, muscle issues, liver issues. We also see that mutations cause neonatal cardiac defects and adolescent myopathies. So riboflavin is so important to our bodies. We need it daily. And so I hope that this was able to bring clarification into what riboflavin does in our bodies.